Alright guys, the last piece of this puzzle. Yeah, maybe you understood. Okay, yeah. We measured the acceleration using the velocity versus time graph, that Logger Pro software. We found the slope of a velocity versus time graph because the slope tells you the acceleration. But I still don't get how we changed the force, or how did we even calculate it, because all we were doing was moving masses around, and I don't know how we had force as that independent variable. That makes sense. It's kind of tricky. So how did we change the force? And how did we calculate it? Well, remember, we had our cart, and it had a little loop-de-doo on that string, and there's the table there, and we just had masses here on this cart. And say we hung like a 200, let's say that this was a 200 gram mass. And you're thinking, okay, yeah, that's a 200 gram mass, but how do we, that's not a force, that's a mass. Well, what we did first was we converted this to kilograms. It's not so hard. We converted this to kilograms by dividing by 1,000. So we had 0.2 kilograms. And that's our start. And you're like, okay, cool. That's converted to kilograms. 0.2 kilograms is hanging off the edge of there, but that's still not a force. Well, to figure out what this, I'll draw the free body diagram here. What is that force due to gravity? Because this is what creates the whole net force on the system, which pulls the cart down, and that's how we measure the acceleration. It's this net force created by gravity, by the Earth, pulling on this 0.2 kilogram mass. So what is that force? How do we calculate that? Well, we use a handy dandy equation. Real simple. Force due to gravity equals the mass of an object multiplied by the acceleration due to gravity. That little g, that's 10 meters per second per second. That's the acceleration. This is the rate at which objects fall and increase velocity as they head to Earth. Yeah, that little g, that's 10 meters per second per second. If I drop something, it's going to be moving 10 meters per second at 1 second, 20 meters per second at 2 seconds, 30 meters per second at 3 seconds. Its velocity is increasing 10 meters per second each second. That's what little g is. Anyways, back to the formula. Fg equals mg. This is our handy dandy formula that we're going to use, and it's as easy as plugging and chugging. This m, remember, that's our mass, and here's our mass right here, 0.2 kilograms. If our mass is 0.2 kilograms, then we have all the elements here to solve for force due to gravity. Our force due to gravity equals 0.2 kilograms times 10 meters per second per second. What's 0.2 times 10? Well, multiplying anything by 10 is really easy. You just have to move the decimal place over. Boom. That's 2. What are the units? Well, the units is force. Yeah, we're in force now. And the units for force, do you remember? The units for force are newtons. So we got a 2 Newton force. That's perfect. That's our first independent variable, our trial 1. We're going to be testing a 2 Newton force. So this is no longer a question mark. That's 2 newtons. And then you'd be measuring the acceleration. Okay, well, that's well and good, you say, but hey, Mr. Ripperetti, what happens if we, take a mass off? If you see we're up here, we take a mass off, we add it. Now there's more. What do I do now? What do I do now? Well, let's just get some more space here. Let me make sure that I'm still lined up. Cool, yeah, so say we have that cart. We have two masses on here. We have a string. And we have two masses hanging off the end now. This one was 200 grams. And this one, let's say that one was 500 grams. Now, or let's say this one was 400 grams. What's the deal here, Mr. Rip? How do we figure out the force? Now, all you got to do is you got to add those together. This is going to be a lot bigger force now. See how I drew the vector a lot longer? Now the force due to gravity is going to be a lot stronger. And so this vector, I'm going to draw a little bit bigger. And we're going to use that same formula, Fg equals m times g. And we look, oh man, 200 grams, 400 grams, what's our mass? I know that g equals 10 meters per second each second, but now our mass, I got these two masses. What do I do? Oh, all you gotta do is add them together. 200 grams plus 400 grams equals 600 grams. Well, that's grams, man. I need to get it in kilograms. So I divide by 1,000 because there's 1,000 grams in 1 kilogram. You can also just use your search Google. Google will tell you, hey, 600 grams, what is that in kilograms? That's 0.6 kilograms. That's 0.6 kilograms. That's the new mass that the Earth is going to be pulling towards it. But what's the force? That's kilograms. We want it in newtons. Well, from the acceleration due to gravity. And remember, that's not this cart does not accelerate at the acceleration due to gravity. That would be free fall, and this was still connected up here. It would free falling is the acceleration due to gravity. That's 10 meters per second each second. The mass is now 0.6 kilograms. And now it's as easy as plugging and chugging. Force due to gravity equals 0.6 kilograms times 10 meters per second. All you got to do when you multiply anything by 10, you just move the decimal place over. Now we have 6. What's the units? Newtons. We have 6 newtons. Oh, great. Now we have changed the force. We had a 2 Newton force. We're going to measure the acceleration using the motion sensor and the velocity versus time, the slope of the velocity versus time graph, and then we changed it to 6 newtons.